Here we are going to have a closer look at angular momentum and spin, where we will focus on some features that highlight the unique properties of these quantities in quantum mechanics. We are going to start by working out the uncertainties of the angular momentum components in these states here. So the states that we singled out as the natural states when we worked in spherical polar coordinates. Then we are going to move on to explore the relation between angular momentum and rotations. And these turn out to be rotations really in our three-dimensional position space. But when we then also extend this to the case of spin, we see that this is indeed very similar to such rotations, but has one very interesting difference. In the main videos, I also mentioned that there's one particular case of angular momentum with L equal to 1, where our description really works with 3x3 matrices and three-dimensional vectors. So we are going to have a quick look at this again, first to just verify some of the statements that I made there. But then we're going to approach this case also from a different perspective. Namely, this can also be obtained by combining two spins, so two systems with intrinsic angular momentum equals to 1/2. And finally, we are going to have a brief look at the relativistic origin of spin. Now, this will be the advanced part. So this advanced part is really more about fundamental aspects, at least from the perspective of this course, while all the other parts really focus on some practically useful aspects of angular momentum and spin. Okay, so let us start by working out the uncertainties of these angular momentum components in the state Lm. So these are the states for which the following features are true. They're really defined as the joint eigenstates of total angular momentum, with an eigenvalue given as h bar squared times L plus 1, and the z component of angular momentum, with eigenvalue h bar times m. And here L is running from 0 over all integers in integer steps. And for any given L, m is running from minus L to plus L in such integer steps, so that there are then 2L plus 1 different values. On ground level in spherical polar coordinates, these states correspond to spherical harmonics. But when you now want to work out these uncertainties, we want to avoid dealing with them directly. Instead, we are going to use the main algebraic properties, including that when we look at the commutator of two such angular momentum components, then this is just going to give us the third angular momentum component. And so, for instance, this relation here tells us that we can write Lx also in the following form. Okay, so this is really all that we're going to use. And so let us start with the simplest case, namely the uncertainty of the z component. So let us first work out the expectation value of Lz in one of these states. So that would be this expectation value here. And then we can use this equation here to replace what we have in the inside by h bar times m. And now this is just a number that we can pull to the front. And we are assuming that all of these eigenstates are normalized, and so the result here is just h bar times m. And now we just carry on with the second moment, so the expectation value of Lz squared. Well, for this we just place Lz squared in here. And now we can use this eigenvalue equation just twice. Because what this really means is that we apply Lz twice to this state. And in the first instance, this just again becomes h bar times m times this state. But this is again a number that we can pull to the front, and then we can apply this operator once more. So at the end we obtain h bar squared times m squared. And then again this expression here, which just becomes 1. So what's the uncertainty then? Well, that's then defined as the square root of the difference between the second moment and the square of the first moment. And this here just turns out to be h bar squared m squared minus h bar m squared. And so this is just 0. And this is indeed what always happens when you work in the eigenstate of a given observable. So let us look at delta Lx. Well, for this we again need two expectation values, and we start with this one here. And now I'm going to replace Lx by the expression given above. Which is useful because Lz now appears in here. And for instance, Lz here is just acting directly on one of its eigenstates. In this case, this doesn't work out in this direction, but it works out in the other direction. Because in the other direction, we still have this equation here. This is very similar what we have done sometimes with the Schrödinger equation, where we let it act on a dual state, and this is then the dual version of the Schrödinger equation. But this simply works for any eigenvalue equations for these Hermitian operators. Right, so what this means is that at this place and at this place, we can really replace these operators by the eigenvalues. And what we then obtain by just continuing this equation is that the h bar cancels. We have a factor of 1 over I that we can pull to the front. And then we simply have this expression here. But this involves here the same operator, so this simply cancels, and therefore the result is just 0. Okay, let's see whether we can do some similar modifications when we look at the other expectation value, which involves the square of Lx. So this would be this expectation value that we can now write in this form here. And then we could of course introduce this expression for Lx at both of these places, but here is actually more useful to just do it at one place, and I'm going to choose this to be this place here. I'm going to extract immediately this factor 1 over I h bar, and then we have the following products of angular momentum components, one's in this order and one's in this order here. Now at this place, this is again acting on this eigenstate here, so we can replace this by h bar m. But here we are not quite at that stage, because the order of these operators of course matters. But here we can again use the commutator, because we can also write this as Lz, Lx. When we then subtract the commutator between Lz and Lx, it's maybe useful when you write this out for yourself to see how that works. But this one here is simply now given by I h bar times Ly. Well, this Lz is then again acting on one of its eigenstates to the left now, and therefore we can replace this by h bar times m. But this then gives us the same expression as we have here with a minus sign in front of this, so these two terms then cancel. And what remains when we cancel these factors I h bar is then simply the expectation value of Ly squared. And this is indeed very natural, because in these particular states there shouldn't be any difference between any features related to the x and the y direction. So this is a useful relation, and we can combine this now with the knowledge that these eigenstates are also eigenstates of the angular momentum squared. Indeed, with an eigenvalue, as given above, h bar squared times L plus 1. And this is then also the expectation value, just in the same way as we discussed above for the operator Lz. But now we can also pull this expectation value apart into expectation values of Lx squared, Ly squared, and Lz squared. And these two are now identical, so this gives us 2 times the expectation value of Lx squared plus the expectation value of z squared, which, as we just worked out, is h bar squared times m squared. And therefore the expectation value for Lx squared is just 1/2 h bar squared L times L plus 1 minus m squared. So this then can be combined into the uncertainty of Lx. But given that this expectation value here vanishes, this is just the square root of this expectation value here that we have just derived. Now this is the uncertainty of Lx, but the same can also be carried out for Ly, and this just gives us the same value, simply because again there is no difference between the x direction and the y direction in these kind of states. And then we can multiply these two, but this is just for completeness because uncertainty principles often look like this. So then we just obtain this expression again. Which is, of course, larger than this expression here. Because here we have IH bar LZ, so we get the expectation value of LZ, which is even just 0. So in this case, this uncertainty principle itself is maybe not so informative, but these particular values of these uncertainties certainly are very informative. So in the states where we know everything about the total angular momentum and the z component, we have uncertainties in the other two components.